Hello students, and welcome to part 3 of the course. Today we're going to be going over capacitance. So in the last 2 weeks we covered two subjects. We talked about Coulomb's law and our electric field around a conductor. One of the things I want to point out is what we were learning from the last 2 weeks. It's going to be very critical for what we're going to be studying in today's lab, which is capacitors. So in Coulomb's law we're learning about forces between charged particles, which is we saw the famous Coulomb's equation, which is important to the physics that we're going to be doing in today's lab. And then last week, we talked about how those charges can have an influence on the environment around them, and about electric fields. So this week, we're going to kind of be applying these two principles, and we're going to be modeling the behavior of a capacitor. So before I get into what a capacitor is, I kind of want to go back to what we were studying last week, right? So if you remember last week, on the second part of our lab, they asked us to put 13 charges. We had 13 positive charges and 13 negative charges. And they asked us to put these charges in basically a line fashion. So we had a line of positive charges and a line of negative charges. Well, you may have noticed that these made two parallel lines, right? And as you kept adding charges, you should have noticed something about the electric field. The electric field in the middle here, these arrows became more uniform, meaning that they were pointing directly to the negative charge. So if you play with the simulation or go back to the software, you will notice that as you add more charges, if you make these lines longer, the electric field in the middle of the region will become very, very straight. And these fringe lines that are kind of pointing away and coming back in, they start to disappear. Another thing that you would notice if you go back and play with the software, if you decrease this distance between these two, those fringe lines almost disappear. So this is a very important assumption that we have to make for when we're going to be modeling a capacitor. So what is a capacitor? Well, a capacitor is basically a device that can store charge, right? So just like what we learned last week about those two parallel lines, we're going to be making some assumptions. So a capacitor looks like this, like those two line charges that we had. One of the things I want to point out again is that the electric field and the capacitor, we're going to assume it's uniform, meaning that those fringe lines, we're going to neglect those. So for our purposes, a capacitor, the plates are they're not placed very far apart from each other for our purposes of when we're looking at a capacitor. Now I want to point out that one side of the capacitor will be positively charged and the other side will be negatively charged. And you can see this here by the electric field lines, right? Remember that the electric field always points towards negative charge. So these arrows are pointing towards this negatively charged plate. So a capacitor is a device that can store electric charge. And you might be familiar with a capacitor, or you might have seen some equipment that has a capacitor, like the old Kodak cameras that were disposable. The flash was actually using a capacitor. When you spin the little knob, it charges the capacitor, and then you click it, and then that's what causes the flash. Tasers are another device that typically they use capacitors, and a lot of circuits use capacitors. Now we're not really moving into simple circuits just quite yet. We're learning about circuits, but I want y'all guys to get in that engineering mindset that that's the direction that we're going to be moving towards. So one of the important things that one might ask themselves about a capacitor is, especially when you're doing circuits, is how much charge can a capacitor store, right? So how much charge, depending on the size of your capacitor, like its area and the distance that they're apart, one might ask is how much charge can a capacitor store? So this is very useful information. So that's what we're going to be modeling this week. So I'm going to give you the equation for a capacitor. And the equation for a capacitor is this, or capacitance is this. It's the amount of charges that you have divided by the electric potential, right, that the capacitor has. So in your simulation, they're going to tell you to set the electric potential, and then they're going to give you, you should know the amount of charges that you're using on the capacitor. So you could very easily calculate the capacitance by plugging it in directly to this equation. Now, we know that capacitance is the amount of charge that a capacitor can store, but what's the SI units for capacitance? Well, the SI units that we're going to be using is going to be a farad. And ferrets are, the symbol for ferrets is going to be a uppercase F. So when you have a capacitor, they might say, okay, you have 20, you could have like a 20 or 50 farad capacitor. That's the units that they use to describe how much charge a capacitor can store. So keep that in mind, that's important. Now, one of the things that I notice that students struggle with typically is deriving equations. Now, in your worksheet this week, they're going to ask you to solve capacitance using two different equations, right? Now, I want to point out that those two different equations are related to each other, and you should get the exact same answer. So in your worksheet, they go through the derivation. I want to go through the derivation, how to get you your other capacitance equation. This should get y'all guys in the mindset of using algebra and seeing how these physical quantities relate and seeing where does the physics come from. Remember, early on in this PowerPoint, I said that we're drawing from concepts from Coulomb's law and our second lab, the electric field, right? So we're already assuming that we have a uniform electric field. That's the principles that we learned last week. And then these equations for capacitance, it's coming from the concepts that we learned from Coulomb's law, right? So we have Q, which is basically the total charges. Oops. So we know that our total charge can basically equal to your charge density times your area, right? So basically we're multiplying this times area to get the total charges for the capacitor plate. And this is all coming from the idea, like this symbol is kind of related to this Q because this was our elementary charge. So Q is just basically quantifying how many charges do we have. Now, we're dividing by electric potential or voltage, right? So how does voltage relate? What is voltage? Well, we kind of learned about voltage last week, right? So your electric potential is going to equal to your electric field, in this case, times the distance here, right? And remember from last week, electric field comes from Coulomb's equation. So this is how all this physics relates. Remember, we might be doing different labs, but all this information that we're learning is building off of each other, okay? So now let's plug these equations in, this Q and this delta V that we learned, and we could rewrite this equation, right? So now this equation becomes this. C is equal to basically Q, but we're just using different symbols because Q is equal to your area times basically your charge density. And now we are doing electric field times this distance. Okay, so again, this is the equation that I just said. So the next thing you may ask is, okay, how does electric field relate? Remember, this is all coming from those Coulomb's ideas. Well, electric field is equal to your charge divided by your permittivity, right? This is all coming from what we learned last week, okay? Your distance is still here too, so it should be able to fit Coulomb's equations, all right? So they're not written explicitly the same, so it gets a little confusing, and sometimes they change these symbols like charge density and things like that, but the concepts are all coming from what we learned in Coulomb's law. So now, if we plug this E into this equation, our new equation becomes this. You'll realize that these will cancel out, and then you're left with your final equation right here. So you guys should start trying to practice on using algebra a little bit to see how these physical quantities relate. I know it's one of the most difficult things about physics. It's very mathy, and sometimes it's not always straightforward. But one of the things I want to try is to make it look simple and for you to have at least a basic understanding of knowing that, hey, these equations are coming from the two experiments that we just learned, or that we just conducted. It might not always be straightforward, right? Because I know math is difficult for a lot of students, but I wanted to try to present it in a way where it becomes clear. So in this week's lab, you're expected to calculate the capacitance by using this equation and this equation. It's one of the questions in your worksheet. So when they ask you, calculate it two different ways, they're asking you to use this equation and this equation. And you may notice that these quantities are all related to each other, right? So they're going to give you the exact same numerical value. So if you do your calculations this week and you're noticing that you're not getting the exact same answer, you're doing something wrong. You're using a wrong constant, or or you're calculating something wrong. So just know that when you do your worksheet, that these two boxed answers, when you do your calculations, they should be exactly the same. Okay? And this is how they are related to each other physically. So that being said, that's what we're studying this week. We're studying the model of a capacitor. Now, I want to give y'all guys a hint for your quiz because I feel like this one is may be a more difficult question because it's a circuit question, but you may see this type of question on your quiz. Now, I know we're not getting into simple circuits just yet in our lab, so you may have seen it in your lecture. Now, a type of quiz question that may be asked is when these are in parallel. We'll learn about parallel and series circuits in another lab, but just know this. When you have something in parallel and you want to add the total capacitance of your whole circuit, it will add normally, okay? Now, we'll go over this more in later labs to come, but just for the sake of your quiz, just note that if somebody asks you if somebody tells you that you have a parallel circuit or these capacitors are in parallel, when you add them, you just add them normally. 0.1 plus 0.2 plus 0.3 equals 0.6. Okay? So just note that when these are in parallel, you just add your capacitors normally to get your total capacitance. Again, in another lab, we're going to go over simple circuits, and it's going to become more apparent, but for the purposes for this week's quiz, this is the only thing that you need to know. When you add a capacitor in a parallel circuit, they add normally, like 0.1 plus 0.2 plus 0.3. This is a very important hint. If you take that note down, you should do well on that quiz question. So again, if you have any questions, feel free to send me an email. I'll just quickly go over this week's lab. It's fairly straightforward. Again, there's going to be two parts. They're going to ask you to adjust some of the parameters, like the distances or like the area. You're going to change the area and you're going to change this distance. And they're going to give you step-by-step instructions, just like the last 2 weeks. You have part 2. Part 2 and part 1, they're fairly similar to each other. And again, you have your worksheet. I think I covered most of the key things for your worksheet in my PowerPoint. But it should be a very straightforward lab. They're going to have you graph in Excel, so please just follow the proper graphing methods. Again, I gave you a video previously for that. But it should be a very straightforward lab. I don't anticipate this lab being very difficult. If you understand the presentation, you should do very well. But again, if you do have questions, feel free to come by office hours or send me an email, and I'll try to respond to you as quickly as possible. And have a wonderful week, students.